Hello, everyone. In this video, Chapter 16, Lecture 4a, I will be discussing the reactions of amines with ketones and aldehydes, as well as amine derivatives called hydrazines with ketones and aldehydes. I will also be discussing the synthetic applications of selections of these reactions. So by the end of this video, you should be able to draw a mechanism for the condensation of amine with a ketone or aldehyde to form an imine or iminium ion. An iminium ion is a derivative of an imine that's positively charged. You should be able to draw a mechanism for the reductive amination of an aldehyde or ketone and explain why this reaction is more selective than direct alkylation of nitrogen atoms. That is to say, there are two different ways we can form nitrogen-carbon bonds. One of them is very easy to do, but not selective. The other, it takes a little bit more work, but is highly selective. We'll talk about what that means. You should be able to draw a mechanism for the Wolff-Kishner reduction of carbonyls to methylene units. Methylenes are CH2s. And then finally, you should be able to decide when to use Wolff-Kishner or another ketone reduction called the Clemmensen reduction. You should be able to differentiate when it makes sense to use one over the other. This will be dependent on the functional groups present in the rest of the molecule that will decide whether or not it makes sense to use one or the other. We'll talk about that at the end of it. So all of the reactions that we'll be discussing in this video rely on the same basic mechanism of condensation. When we say condensation, this often refers to reactions that generate water as a side product. In this case, the reaction of aniline with a molecule called acetaldehyde starts with the nucleophilic addition of nitrogen to the aldehyde carbon. A mechanism with ketones is identical other than the fact we start with a ketone. After this attack on the aldehyde, we generate what's called a Zwitter ionic intermediate. Zwitter ions are ions that have both plus and minus charges on the same molecule. In this case, we have a nitrogen cation, an ammonium, and an oxygen anion, like this one shown here. In the next step of the reaction, a general base B will deprotonate the ammonium to render a neutral nitrogen and maintain the oxygen anion. This also generates an equivalent of the protonated general base, which I'll draw as this here. In the next step, our oxygen anion deprotonates this to afford what is called a hemiaminal. You may note as I work through this that this mechanism is very similar to acetal formation. However, unlike acetal formation, it is considered permissible to use the nitrogen lone pair to eject a hydroxide leaving group, leading to what's called an iminium ion. The reason for this is that the nitrogen lone pair are held less closely to the nitrogen than in an acetal reaction. And this is a better driving force for the loss of a hydroxide leaving group. Hydroxides are not good leaving groups generally, but the greater stabilization of the lone pair in the cationic intermediate here makes this step more feasible. And to highlight that, I'm going to draw a resonance structure here that shows an alternative formulation or drawing. Again, this is the same molecule, just a different way of representing the electrons. The nitrogen lone pair here are much better at donating onto this carbocation, so they facilitate the loss of a worse leaving group. This hydroxide ion then yields the product by deprotonating the iminium proton to generate the neutral imine. This is the formation of a standard imine using standard condensation reactions. You can imagine that the evolution of water may render this reaction reversible. That is, you could draw the water attacking the imine here and so forth. This is indeed reasonable, and in imine condensations in the lab, you often need to remove water to push the reaction forward. That is, to convert it all to the imine product. This reaction is not limited to just primary amines. This reaction is also common and, in fact, easier to do with what are called hydrazine derivatives. Hydrazines are molecules where there are two amines bonded to each other. This renders both of the amines more nucleophilic than just a regular amine. So if we rank them in their nucleophilicity, a hydrazine is more nucleophilic than an amine. This is what's called the alpha effect. And this means that the heteroatom attached to the nucleophilic atom donates extra electron density to make it more ready to attack electrophiles. So in the condensation of a molecule called semicarbazide with a ketone, in this case cyclohexanone, the attack starts just the same as the previous mechanism. And we'll generate another Zwitter ionic intermediate. You should know what a Zwitter ion is by the end of this video. Another example of a Zwitter ion, or common Zwitter ion, is an amino acid. And the presence of Zwitter ions can be important in biochemical reactions. So again, this is much the same as the previous mechanism. You may note that as I draw this, sometimes I will draw in lone pairs and sometimes I will not. When I draw in the lone pairs, it is for emphasis to help make the reaction more clear. If I don't draw them in, they are implied in many other cases based on the formal charge. And again, the nitrogen lone pair is better able to eject a modest hydroxide leaving group than, say, an oxygen analog. Again, we get to our aminium intermediate as well as a hydroxide ion. The protonation affords the product. Important, while this mechanism may be the same, some of the vocabulary is important to learn. By the end of this video, you'll also want to know what a hydrazine is, and you'll also want to know what the product of a hydrazine condensation with a carbonyl is, which is a hydrazone. A hydrazone is like an imine, but it has another nitrogen attached to it. So why do we care about all this? Why are we learning about these reactions? You could imagine that you could generate a carbon-nitrogen bond through simple SN2 alkylation. However, this is a problem for practical reasons. Organic chemists would rarely generate carbon-nitrogen bonds using alkyl electrophiles such as this methyl cyclohexyl bromide on the bottom. Because when you do this reaction, once you add the alkyl group here, the amine actually becomes more nucleophilic than the original starting material in some cases. What this can do is then you start adding multiple groups to the amine, and the rates of these reactions are dependent on the nature of the electrophile and the nature of the nitrogen nucleophile. But suffice it to say that a mixture of products is highly undesirable to a synthetic chemist. If you're just trying to synthesize the secondary amine compound here, you'll have a very difficult time because you'll generate some tertiary amine and you'll have some primary amine left over. This is highly undesirable. What's more is that you can inadvertently form some salts, such as this, what's called tetraalkyl ammonium down here, highlighted again in the blue. So this scenario is highly undesirable to an organic chemist. And so they've developed new ways of just adding a single carbon-nitrogen bond. And this can occur through imine condensation reactions in a reagent called sodium cyanoborohydride. Sodium cyanoborohydride will react with an iminium ion to deliver a hydride equivalent to the iminium. Just as a reminder, when we talk about hydride versus hydrogen atoms versus protons, we're changing the number of electrons we're referring to. A hydride is what we think of as an H minus, put it in quotations. That would be a hydrogen with a lone pair. A hydrogen atom is a hydrogen where we're transferring an equivalent of a hydrogen and an electron. And then a proton is just an H plus, where we're reacting some sort of Lewis base with a proton, or with an H plus. Sodium cyanohydride is a stabilized version of a hydride. You'll note that the bond from the boron hydrogen attacks the iminium carbon. So the condensation mechanism of this step is much the same as what we discussed in the first imine condensation example. We lead to our zwitterionic intermediate. This is deprotonated. While this may seem repetitive, this is an important mechanism to know. While I write this out, it might be important to comment again on the difference between this and an acetal formation under acidic conditions. In this case, it's okay to generate oxygen anions. We want to avoid that when we're drawing mechanisms of acetal formation under acidic conditions. And again, this nitrogen lone pair aids in the removal of the hydroxide to give, in this case, the key intermediate iminium. And as drawn above, this is the key step. Where we draw in a rare example of the bond of a hydrogen attacking something to afford the product. If we were to highlight where this hydrogen came from, I could draw it in red. It would be one of the two here. All right, so let's investigate a synthetic application of amine condensation reactions. Specifically, we'll be talking about a synthetic application of hydrazone formation from hydrazine and this cyclohexanone derivative here. This reaction is called the Wolff-Kishner reduction. You'll note that we've replaced our carbonyl with a CH2. Again, our skeletal structure is hiding that we now have a CH2 there. This isn't an error. The carbonyl is not supposed to be there. This can be broken up into two steps. The first step is to form the hydrazone. And the second step is to use this hydrazone to facilitate protonating the carbonyl carbon. We put protonating the carbonyl carbon in quotations because, as you'll see in a minute, it's much more complicated than that. So this reaction also starts with the attack of the carbonyl by a hydrazine. Again, hydrazine is this molecule here. To afford the zwitterionic intermediate. This mechanism proceeds through the same pathway as the previous condensations we've talked about with primary amines as well as semicarbazide on the previous slide. I'll just work through this quickly. Remember again that hydrazones are generally, hydrazine is generally more nucleophilic than a primary amine. This gives us our neutral hemiaminal-like intermediate. Leading to the key hydrazone. So this is step one of the Wolff-Kishner reduction, getting to this neutral hydrazone. You'll note in the above reaction that we actually have potassium hydroxide in this, KOH. This potassium hydroxide is a decently strong base and is used to initiate the second half of the reaction. Which is to start the protonation of the carbonyl. When we say protonation, we're going to draw BH here. Is sort of a general acid. In this reaction, it could be anything. It could be water, so forth. What we think about is that this lone pair up top, up here, this is donating down to increase the nucleophilicity and sort of reverse the normal polarity of, say, a regular imine. This is a hydrazone, so it's different. This allows us to put a proton on the alpha position here. A generic base deprotonates this. We'll write B, but this is because we use potassium hydroxide, is very likely hydroxide. Oops, sorry, I just realized I forgot to get rid of this nitrogen, or this hydrogen here. It was never there. You'll see over here that hydrogen was never there. Just realized that mistake. And this leads to this intermediate here. And this sets up what looks like an unusual step. And that is deprotonation of this nitrogen here, again, by a base, general base B. These electrons fall down. I'll draw the lone pairs in for emphasis. And this causes the formation of a highly unstable anion. This anion doesn't have, it has resonance with the benzene ring, but it doesn't have any carbonyls or anything else to help stabilize it. So why does this happen? Well, the key in understanding why this step happens is in balancing the reaction. We actually form an equivalent of dinitrogen. And the bond in dinitrogen is extremely strong, and it's a gas. When we form gases, this is entropically favorable and helps drive reactions forward to the product. This reaction is finished out by protonating the anion with general acid A to lead to product. This installs a methylene unit here where we can now clearly see we have the CH2 at that position. So this reaction is broken up into two parts. Just to recap, it's hydrazone formation, which is very similar to the imine condensation we talked about on the first slide. After that, we use the lone pair on the hydrazone to facilitate the protonation of the alpha carbon to the nitrogen. This then sets up a base initiated extrusion of dinitrogen here. which drives the reaction forward to allow us to quickly protonate that unstable anion, resulting in the net 2 hydrogen reduction of a carbonyl. This brings us to our last slide, which is distinguishing when to use another type of reduction called the Clemmensen reduction. The Clemmensen reduction is a reduction that occurs under acidic conditions using something called zinc-mercury amalgam. You see it written like this. This is zinc-mercury amalgam. An amalgam is a homogeneous mixture between two metals that has fluid properties to it. What this does is it allows our zinc, which is a reductant, to help reduce our carbonyl back to a methylene, just like the Wolff-Kishner reaction. But what's important is that the Clemmensen reduction is a reaction that is quite able to tolerate some base-sensitive functional groups. So when thinking about synthesis, sometimes a reaction we want to do will react with another functional group in our molecule. So with this ketone and ester derivative over here, the Clemmensen reduction occurs under mildly acidic conditions, HCl, with zinc-mercury amalgam. It reduces the carbonyl, but it doesn't touch the base-sensitive acetate ether here, which is in the green box. If we were to do the Wolff-Kishner reduction, which is under highly basic conditions, this would hydrolyze the ester. And this would be considered bad if we wanted to maintain this ester on our molecule. In contrast, the Wolff-Kishner reduction is compatible with base stable groups. So in this case, this acetal is stable to bases and would easily survive a Wolff-Kishner reduction. However, the acetal group, as we learned in the previous lecture, is not acid stable. Acids decompose acetals in the presence of water. And the Clemmensen reduction would cleave both our acetal as well as the intermediate ketone. So you may be wondering, if we just cleave the acetal, why does a methylene show up there? Well, it goes through this intermediate here. And then does a Clemmensen reduction on both. So this example is used just to highlight that when we think about synthesis, we want to make sure that our reactions we're doing are compatible with other functional groups of the material. And the correct choice of them, of what reaction to use, will depend on what else is on the molecule. For the Clemmensen reduction, we have acid stable groups, is what we want. For the Wolff-Kishner reduction, because it's under highly basic conditions, we want groups that are stable to bases, like acetals.